Alright, ladies and gentlemen, welcome back to this Athenian Stranger tutorial video where today we are going to learn about slope. These are the video notes, so if you weren't able to be in class or if writing notes in class is not something that you can do while paying attention, I understand. I feel your pain, so that's why we're doing the video notes. So this is not a complete replacement for being in class, but I'm going to go through these notes, and the expectation is that you are going to write down what you see here and that you'll watch these notes on video so you can reinforce the learning for your homework. Just right away, I want you to notice how algebra has changed. So we have here a lot of writing and not a lot of math. So for some of you, that will be a welcome reprieve. Okay, so the header for the page is called Linear Equations and Functions, find the slope. And the Roman numeral I, that means, 1. And that section is titled, What is Slope? Okay, subpoint A. Formally, the slope is the rate of change in the dependent variable with respect to the independent variable. Subpoint 1. The dependent variable of a function is the one whose value depends upon the other variable, called the independent variable. And here we've noticed that the dependent variable is the y-axis. Okay, subpoint 2. The independent variable is the one whose value does not change based on any other variable. And here we've noted the independent variable is the x-axis. Now we move on to examples. Okay, this is section 3 or subpoint 3, section A, lowercase a. Okay, here's an example. The size of tomatoes and the amount of rainfall. Think about it for a minute. If there's no rainfall, your tomatoes will not grow. Okay, they need water. So the size of tomatoes depends upon the amount of rainfall. So the dependent variable is the tomato size because it depends upon the rainfall. And we put that on the y-axis or the vertical axis. So tomato size depends on rainfall. And the independent variable is rainfall. And you could prove this by asking yourself the question, does rainfall depend on tomato size, or does tomato size depend upon rainfall? And that's how you kind of figure out which one goes on the y-axis, which one goes on the x-axis. So the independent variable is rainfall because it doesn't care what the tomato size is, but the tomato size cares a lot about what the rainfall is. That's how you distinguish the two. So let's get to how you compute the slope. The slope is found by taking the ratio of the change in the tomato size over the change in the rainfall. And here, this little triangle means change. So that little triangle means change in tomato size. And in Greek, that little symbol, that little triangle means delta. And delta means change in math. All right, so change in tomato size over change in rainfall. Take notice of this. If the ratio that you get is greater than 1, okay, in other words, if the slope is greater than 1, that means that the change in the tomato size outpaced the change in rainfall. Or you could say it another way, the change in the tomato size exceeded the change in rainfall. In other words, the numerator is bigger than the denominator. That's when the slope is greater than 1, when the numerator is bigger than the denominator. Or the change in the dependent variable is greater than the change in the independent variable. Okay, here's another example. Brain size and stage of pregnancy. Now, I'm not here to get into some kind of argument about pro-life or pro-choice. That's not for this class. I'm merely trying to bring in something from the real world that you might be able to relate to. So brain size and stage of pregnancy. So we would say here that the brain size depends upon the pregnancy stage. In other words, pretty simple. When the developing fetus is very small, its brain is very small. Over time, that baby will grow and its brain size will get bigger. So we say the brain size depends upon the pregnancy stage, which is just another way of saying time. And we note here that time is always independent. So we can say that the size of fetal brain depends on the stage of pregnancy. So to compute the slope of this situation, we would say that the change in the brain size divided by the change in time will give you the slope, or the rate of change. Next page. Okay. So this is major subpoint B. Informally, we call the rate of change slope, especially when looking at a picture like this. All right? And here I've got an XY graph where I've labeled the y-axis as the dependent variable and the x-axis as the independent variable. And I've got an equation for the line, y equals mx plus b. This is the slope-intercept form equation of a line. We'll talk about that later. But the key point here is that I've plotted 2 points on this line, and I've labeled those points x1, y1. And I've labeled the second point x2, y2. Over here I've noted that the rate of change, that is the change in y over the change in x, is the slope. And we call the slope m. And you'll find that right here as well, m. Okay? All right, so down here I've said that the change in y over the change in x is equal to the new y value minus the old y value over the new x value minus the old x value. Now that's just a common way of saying it. It helps me keep it in mind because that means that this is y2 minus y1, in other words, new y minus old y, over x2 minus x1, new x minus old x. So this is where the slope formula comes from. Okay, and if you're into formulas, that's m equals y2 minus y1 over x2 minus x1. In other words, the change in y over the change in x. Subpoint 2. Sometimes you will hear the slope called rise over run. This is just another way of saying the change in y over the change in x, or the vertical change over the horizontal change. But this rise over run notation is really only useful when you have a grid or graph paper. Okay? Otherwise, you can't really count the change that way. Okay. Subpoint C, finding the slope from coordinate pairs. Let's say you're given 2 coordinate pairs, x1, y1, x2, y2. In that case, the slope equals m equals y2 minus y1 over x2 minus x1. Here's an example. Find the slope of the line passing through these 2 points, negative 2, 8 and 5, 16. So here I've got the steps. The first step is to label the points, and here I've rewritten the points out and I've labeled them x1, y1, x2, y2. Now plug those into the slope formula. y2 minus y1 over x2 minus x1 equals 16 minus 8 over 5, pay attention here, minus, and then we just plug that point in, so it's negative 2. 16 minus 8 over 5 minus negative 2. So we'll rewrite that 16 minus 8 over 5 plus 2, because 5 minus minus 2 becomes a plus 2. Minus minus becomes plus, and that gives us 16 minus 8 is 8. 5 plus 2 is 7. So the slope here is 8 over 7. 8 is the rise, 7 is the run, 8 is the change in the y variable, 7 is the change in the x variable, 8 is the change in the dependent variable, 7 is the change in the independent variable, 8 is the vertical change, 7 is the horizontal change. 1,000 different ways to refer to slope. Let's move on. Okay, this is the final part. Subpoint D, finding the slope from a table of values. This is where the real world stuff kicks in, and I think you might find this interesting if you find astronomy as fascinating as I do. So here's an example. What is the speed of this galaxy? And here we're presented with a table of values. This is how math is going to look in the real world. So here is the galactic distance, Ly, that means light year. Be careful here. Light year doesn't mean time. Light year is a measure of distance. Okay, so the galactic distance, we've got 2, 6, 10, and 14. And then it says time, that's the other column, in seconds, 0, 3, 6, 9. Okay, so here are the steps. First, you calculate the change in distance. That would be the change in the dependent variable. So all I did here is I wrote out all of those distances, 2, 6, 10, 14, and then I measured the change in each one from one step to the next. So this was plus 4, 2 to 6, 6 to 10 was plus 4, 10 to 14 was plus 4. Next, you calculate the change in time. Okay, that would be the independent variable. These are in seconds, so 0 seconds, 3 seconds, 6 seconds, and 9 seconds. And you see here that the change between each point is plus 3, plus 3, plus 3. Okay, so now you calculate the ratio of change. So you just put the 4 over the 3. Okay, because that's the change in the y over the change in the x. The change in the galactic distance over the change in time. And we see here are our ratios, 4 over 3, 4 over 3, 4 over 3. And we just want to note that 4/3 is equal to 1.3 repeating, or 1 1/3. And now we can draw some conclusions. So, 4/3 is the rate of change in distance with respect to time. In plain English, this means the galaxy is traveling at a speed of 1.3 repeating light years per second. Okay, and this is another point. You can tell this is linear because the rate of change never changes. It's 4/3, 4/3, 4/3. And we call this constant rate of change, or CROC. Might be something you've heard before, CROC, CROC. Now here's a little brain teaser for you as we close out this video. Can you predict how far the galaxy will have traveled in 5 minutes? All right, so I'm going to let you think about that for a second. And if you would, please post the answer in the comments section. Can you predict how far the galaxy will have traveled in 5 minutes? Think about how you might figure that out and put it in the comments section. All right, so this is the end of the notes for slope, and I hope you all learned something. If this was helpful, please give a thumbs up. Remember to leave your answer to this question here in the comments section, and make sure you subscribe to the channel so you are always updated when I release new videos. Thank you.